So I want to talk a little bit about ionospheric convection, but I wanted to say just a couple of things about Bill Hansen. AE was launched in 1973, AEC, and that was the same year that I came to UT Dallas as a postdoc. And I joined the mix of AE scientists, Bill Hansen, Nelson Spencer, Paul Hayes, George Carrigan, John During, and other people. And that group of people were remarkably generous. They were well-established scientists themselves, but they gave postdocs like myself and Bill Peterson, who joined that team, and we both agree, I think we were like 15 or 16 at the time. And they gave us a remarkable opportunity to be involved in this new mission. And I personally was involved with Bill Hansen, whose computer skills were limited, to say the least, I have to say. At least his digital computer was limited. But his gastric computer was exceptional, perhaps the most exceptional computer I've ever come across. And he lived in this analog world because he had a very good computer that could relate to things that he would done and things that would he'd had encountered. And so a visit to his office would look like this. He had this really quite remarkable filing system that was everything was referenced by pile number and distance down the pile. But it was unbelievably accurate. And so you could go in and ask him about a certain topic, and he'd say, and he'd reach over pile number 3 inches down, out of paper, and here it was. And within, a couple of papers, it was right there. I came to value that filing system of his, which was in his head and related to this analog pile of papers, which humorously, only humorously, after he died and we had to clear out his office, we actually had to chisel the papers off the floor because the people that waxed the floor were told, "Don't move my piles." So they just waxed around those babies. And so it was quite amusing. Bill had such a great gastric computer that his key training for me was I'd run ideas by him, and he would have this phrase, "Doesn't sound right to me." And that phrase from Bill Hansen meant, "Go back, it's got to be wrong." And so he had very little tolerance for lack of rigor when it came to thinking, and so he was always a very good judge of what's going on. The other thing he gave me essentially to do was make the drift meter and RPA combination, this little device that would measure convection, make that work for AE. And I'm happy to say he was right, that when he said this device will probably tell us a lot about convection, and I'll bet that almost all of you have at one time seen these results from these devices that have flown on AE, DE, DMSP, ROCSAT, San Marco. I mean, just on almost every ionospheric dynamics mission has flown a device like this, and the availability of the data has made it readily available to everyone who's benefited greatly from it, not the least of which has been me, who've been able to increase the capabilities and develop the sophistication with which we produce that data to enlighten us about ionospheric convection. So I wanted just to cover 3 things here, really. One, a little discussion of the ionospheric convection and the convection drivers, something about the variability in the convection pattern and how dynamic it is if we look at it now. So to make a progression from kind of a static picture to a more dynamic picture. Some effects of that ionospheric convection on just 3 things that I'm going to cover briefly, but I'm sure it will be covered in more detail by other talks. And then, just lest we think we're all done, a little discussion about what to do. So my first picture here is just our pictures of the ionospheric convection pattern that come in different flavors. On each of these pictures here, there are references to published material, but at the top here is, on the left, is data from a AMI, which is an assimilation model, which takes measurements of magnetometer or current variations in the current layer of the ionosphere. Also assimilates electric field data or plasma flow data similar to what you see here. And tries to produce a global representation of our convection pattern in terms of an instantaneous electrostatic potential distribution. And that same exercise can be done quite readily now by a fairly vast array of HF radars. This is from SuperDARN, where all available measurements from the SuperDARN arrays, which are distributed in the northern and in fact in some in the southern hemisphere, in the northern hemisphere to produce, again, an instantaneous picture of the convection pattern. And now you can go visit Amy, or you can go visit the SuperDARN site, and you can get updated visualizations of an instantaneous potential distribution like this from these various sources. And so this is our way of describing how the plasma in the high latitude ionosphere moves. It moves along these convection, these trajectories, which are electrostatic potentials. We can take many, many measurements of those velocities and convert them into an average description of that potential distribution, and then sort the behavior of that potential by drivers, in this case sorted by the interplanetary magnetic field clock angle. So this is By positive and By negative over here. This is for Bz negative, and this is for Bz positive. I've taken the liberty of cutting and pasting pieces of Weimer's paper here. And so what you can see by now is a fairly familiar but fairly sophisticated description of the potential distribution for different orientations of By when Bz is negative, and then the appearance of multi-cells or cells that circulate in the opposite sense at high latitudes when Bz is positive. And again, these are average pictures of the convection, things that we know well, I think. And it's sort of an image of in your head of what the convection trajectories in the ionosphere look like. And the message I wanted to deliver today is that they don't look like this. Okay, so a little bit more on the convection drivers. If you take an instantaneous cut, or almost instantaneous, 20-minute cut across the high latitude ionosphere from dusk to dawn, then you'll see a characteristic two-cell convection pattern with regions of sunward flow at dusk and dawn, and anti-sunward flow in the polar cap, which is a standard two-cell convection pattern. Simultaneously with that, DMSP measures the precipitating electrons and ions, and if you look in detail at the boundaries of where these ions and electrons appear, which are pretty good markers for the topology of the magnetic field. So where these electrons and ions appear, the magnetic field lines, that is a line that traces everywhere tangent to the magnetic field, is a closed field line. And if you look at these boundaries, you'll see that they're offset on both the dawn and the dusk side. And in fact, this description of the boundary locations holds up at all local times. If you look statistically at the location of the convection reversal boundary, shown here, and the location of the particle boundary, you'll see that it consistently appears at higher latitudes. And so this is a signature of two drivers for the convection. One that provides all the organization by the IMF, which I showed previously, which I'll call connection to the interplanetary magnetic field, and one that's more related to some kind of viscous interaction, although we know it's not traditional viscosity, but some kind of viscous boundary layer at the edge of the magnetosphere that, if we do an analysis, provides somewhere between 5 and 10 kilovolts in the total potential that you can observe across the polar cap. If we put those two stories together and look at where the magnetic field lines in the magnetosphere and the solar wind connect, lots of advances have been made in identifying where these regions of merging and reconnection are that drive the two-cell convection pattern that's dependent on the IMF, and where this viscous layer is. And we can draw this picture of those two drivers for northward and southward IMF. So on the left here are these two drivers operating for southward IMF that produce this characteristic two-cell convection pattern. Merging and reconnection is shown in red, and this blue circulation cell here in the viscous boundary layer is in blue. And for northward IMF, the draping of the magnetic field in the magnetosheath produces a merging region that's attached to the night side here. And the passage of the interplanetary magnetic field around the planet, around the magnetosphere, causes a recirculation of open flux. And this viscous interaction, this viscous cell, of course, continues, could be modified by interplanetary magnetic field conditions. But these are the two pictures that give us the convection pattern, and it's our image of how convection works, how the connection to the interplanetary magnetic field drives convection in the ionosphere for southward IMF and northward IMF, with various complications associated with the transitions. So this is our picture of the interplanetary, of the interaction. But I want to talk a little bit more about the merging and reconnection, this driver, which varies dramatically from southward to northward IMF, and what we know about that. So lots of advances have been made, not the least of which is the distribution of HF radars around the surface of the Earth that allows us to locally look at the convection just by looking at the Doppler-shifted echoes from moving plasma. And when we have the opportunity to look at those Doppler-shifted echoes across the day side, what we find is rather than a uniform flow that just goes poleward, that flow is intermittent. It goes in flow bursts that last for 15 to 20 minutes, where the flow is quite large, and then the flow is abated. And you can see this in multiple beams in the radar. This is just one example that I picked from a publication by Chisholm. That can be due to periodic changes in the merging rate over a fairly narrow region, and changes in the flow angle over a similar narrow region. So this steady state picture of just merging or interconnection between the interplanetary field and the magnetosphere on the day side is not one that stands up under scrutiny from detailed measurements where you can dwell in the region for a long time. Likewise, on the night side, if you do a superposed epoch analysis and you just try to isolate the difference between a steady state configuration of the convection on the night side, which is shown in the top panel here, and the changes in that convection pattern that are associated with substorm onset and development, then what we see is that this steady state convection pattern has superimposed on it another zonal circulation of plasma across midnight here. So what we see is that the reconnection region is also not a steady state phenomena, that it's interrupted or superimposed upon a steady state is this enhancement in zonal flows that appear and disappear as substorms occur. So we still have a superposed epoch analysis or some more analysis to do to define what these flow circulations look like on the day side, and I'll come back to that in a minute. So the first picture I want to have you appreciate that this steady state distribution of equipotentials is not how the plasma or how the electric field and the plasma move and behave. So this is a plot from DMSP data as the DMSP satellite moves from dusk to dawn across the high latitude northern hemisphere. And in this case, every pass for a month is just turned on its side and plotted as a function of UT. And so what you can see in red here is this region of anti-sunward convection associated with the polar cap. Because of the wobble of the magnetic pole around the geographic pole, the sampling in magnetic latitude has this longitude dependence where the satellite moves back and forth like this. But you can clearly see the polar cap boundary, or the convection reversal boundary, which is shown in black here, which is the transition between the blue flow, which is the sunward flow in the auroral zone, and the red anti-sunward flow in the polar cap. The other boundary you can see is the latitudinal extent of the convection pattern, and we determine this, or I should say one of my students determines this, by looking at the gradient and the magnitude of the flow as a function of latitude. And this green boundary, where you can determine it, shows the low latitude extent of the convection pattern. And you can see it varies greatly from maybe 60 degrees all the way down to 40 degrees and even further in some fairly large geomagnetic storms. This is not a period where the storm activity is particularly large. DST gets to minus 80 here. But what you can see is large dynamical changes in the convection pattern that happen over time scales of a few hours. First, you can see the expansion of the polar cap boundary associated with this storm event here. You can see that occur on the dusk side and the dawn side. You can see the expansion of the low latitude extent of the convection that occurs both on the dusk side and the dawn side. And then if you look carefully, you can see places where the boundary between the convection reversal boundary takes a step, moves up in this region here, and then back down here and up and so on. So here you see all red, that's in the polar cap. Here in this same region, it's all blue. That's the auroral zone. And these motions of the boundary are well correlated with this red trace here, which is the Y component of the IMF. And so the dynamics of the convection pattern are as follows. The whole pattern expands and contracts like this. The auroral zone expands to lower latitudes and contracts like this. And within this polar region, the entire convection pattern moves around, reorients itself according to the direction of BY. Okay, so all these motions are happening on time scales of 20 minutes or so, the response time of the ionosphere to changes in the interplanetary field. So that's the thing to remember. On the day side, I want to look at it, on the night side and the day side, I want to see if we can see these reactions a little bit more. On the night side, if you actually look at the location of the polar cap boundary and try to do this superposed epoch analysis and ask what happens, then what you see is that during a substorm event, the polar cap boundary, which is in black here, retreats to higher latitudes. So this is consistent with during a substorm, you take open magnetic flux and turn it into closed magnetic flux, and the polar cap contracts as a result of that, but it contracts much more dramatically at midnight than it does at dawn and dusk. If you look at what happens to the polar cap during these flow bursts on the day side, this is a plot that just shows all-sky imagery associated with the flow bursts, and you can see these flow bursts in the 6300 emission. But what's more important, I want to focus your attention on, is during these flow bursts, the low latitude boundary here moves to lower latitudes. So when you add open magnetic flux to the polar cap during a merging event, then the polar cap boundary gets bigger, or at least on the day side, and expands to lower latitudes. And this happens on timescales of 20 or 30 minutes. And on larger timescales, associated in an hour or so, if you look at the entire size of the polar cap, which is in these regions here, this is obtained from space-based auroral imagery of the polar cap, and you look at the size of the polar cap compared to the magnetic activity events, then during the onset of magnetic activity, a storm, the polar cap boundary expands, and then as the DST declines, a recovery phase, the polar cap boundary recedes to higher latitudes again. So there's an expansion of the boundary and a contraction of the boundary. Expansion, contraction. And so this expanding, contracting model has had quite a lot of traction, and you probably recognize this as some average look at the convection pattern. But just for your picture, what I've done is added some extra circulation here that's associated with a dayside merging. And if you add those together, now you get one of these convection trajectories that looks more banana in shape. This may be called a convection throat we saw in the mid-70s. But it's something that you see in almost all the time when you look at the convection pattern on an individual basis. But if you average these things out, you see a much wider convection velocity. And it's because that cell that I just added is a temporally varying feature. Okay, so I want to just finish with some effects of the convection. Just to point out that on the day side, this temporally varying convection involving large convection speeds puts a temporally varying electromagnetic energy flux, a frictional heating rate, if you like, into the atmosphere. You can see the very large deposition rates in this little red dot here. And as a result of that energy deposition, the ionosphere expands and produces very large fluxes out of the ionosphere. Here's 10 to the 8. This is per centimeter squared. You need to multiply by 10 to the 4 to put this in the same scale as that used by Andy Yao previously. So these large convective flows produce very large outward fluxes through 1,000 kilometers. So this is ionospheric outflow. I just want to point out that almost equally large fluxes through 1,000 kilometers are seen coming back down in the polar cap. And so the ionosphere expands and contracts and expands and contracts as it's convecting, and some small fraction of that flux ends up in the magnetosphere. In terms of the distribution of plasma, I just want to point out here that when you have this instantaneous picture of the convection pattern, in order to relate it to the behavior of the plasma, it's essential to add co-rotation to that convection pattern. And when you do that, because the magnetic pole rotates around the geographic pole, you'll get two quite different pictures of the convection pattern depending on the UT. So for example, here's 12 UT, and you can see a stagnation or rotation of the flow in this region here. And at 18 UT, this same region is up here at 15 UT. So it moves from midnight to 15 UT in 4 hours, or 15 local time, in 4 hours of UT. In this region here, you see strong poleward flows through that are essentially meridional, and at 12 UT, you do not see those large meridional flows. And so the plasma flow is quite different. And that produces two pictures of the number density. These are two convection patterns. This is our two plots of NMF2, courtesy of Bob Schunk, for these same, approximately these same UTs and same patterns. And you can see here where the plasma rotates near midnight, there's very large, low densities, which don't exist for this pattern. And for this pattern, where there are strong meridional flows, there's this so-called tongue of ionization, which is absent at this UT, because the configuration looks like this. So the picture of the plasma density is very highly UT dependent because of the interaction of that convection pattern with co-rotation. So co-rotation always has to be added to the convection. And then finally, and this is just food for thought, I just want to show you these two plots here that you might look the same and say, hey, these are pictures again across the equator this time of convection in the polar cap and then convection in the auroral zone, these red and blues. The difference is in the scale size of the velocity and the fact that this is the plasma velocity and this is the neutral velocity. And so these velocities in the ionosphere at these latitudes are large enough and sustained enough to put their imprint in the neutral atmosphere. And once they do that, of course, the time scale for changing this guy is minutes. The time scale for changing this guy is hours. And so now they can compete or reinforce with one another. And I think I'll just stop right there with just some outstanding issues. So I think hope I've convinced you that there's a very large relative motion of the plasma and the convection boundaries, and whether the plasma flows across these convection boundaries or not is determined by whether there's merging or reconnection. So if a boundary doesn't correspond to a merging or reconnection region, if the boundary moves, then the plasma must move with the boundary. Presently, that's not established, but we need to be working on a constellation or some multiple measuring strategy to see if we can measure the plasma velocity with respect to the boundaries. This relative motion of the ions and the neutrals that I just showed you is the determining factor in determining the effective resistance of the ionosphere to the thermosphere. And so understanding the altitude distribution of the relative ion-neutral velocities is essential for us to be able to determine what's the nature of the electromagnetic feedback between the ionosphere and the magnetosphere. And we haven't done that yet. And in terms of plasma outflow rates, the effects of frictional heating electron precipitation and photoelectrons in the different regions in the aurora zone and the polar cap, in my view, is still an open issue of whether the ionosphere controls the changes in the flux that is available to the magnetosphere, or actually changes how much flux is deposited into the outer magnetosphere. Thank you.
We have time for just a couple of questions. We're running a little bit late. I think I saw your hand up first, Tom.
So I really like this idea of inferring reconnection effects and geometry from the flows. And I wondered if you can take it further by sort of analyzing the 2D patterns, maybe once they're better observed with constellations, and asking the question, how extended and what shape does the reconnection feature have to have in order to account for those things?
Yeah, I think you, in principle, you can do that. Some work has been started in that by using auroral imaging and taking the shape, if you like, of the polar cap boundary from the auroral imagery, and looking at the time rate of change of that area, and the time rate of the change of that area should be equal to the net flux addition or subtraction from the polar cap. In terms of the shape, then the models that we're using at the moment assume the boundary is circular simply because that's the easiest geometry to solve Laplace's equation. But in principle, you don't need to do that if you knew something more about the actual shape of the boundary.
Yes, with regard to your first bullet up there, it's often said that the ionosphere is incompressible, and of course the divergence of the convection velocity is 0. But in regions of intense ionospheric outflow, the plasma is not necessarily incompressible because some of that fluid that's coming in horizontal goes up the field line. And so the relative motion of plasma and convection boundaries can be quite different in those regions.
Okay, I guess depends whereabouts you are in the ionosphere. If we're below 1,000 kilometers, then I think the diamagnetic currents from the pressure are essentially negligible. And so I don't want to do it, well, we could do it in public if we got enough time. I don't want to disagree with you, but I think it certainly is true. Where the plasma is incompressible, I think, and so if you have two flows that are coming together like this, they must be diverted horizontally. That region of diversion can be quite small, in which case the horizontal flows are large, and the frictional heating rate is then large, and so there is an expansion of the plasma along the magnetic field line. But in terms of the convective flow that is perpendicular to B, I think in the ionosphere, E is minus V cross B is pretty close. There are diamagnetic currents associated with the pressure gradient, but they're very, very small.
Yeah, I'd just like to echo one of your final points about the fact that the magnetosphere can drive the ionosphere with a time scale of the order of minutes, but for the ionosphere to drive the neutral thermosphere takes of the order of hours. And this is an important point that's often overlooked in analyzing data. It's particularly important at the outer magnetospheres, where most of our observations really come from remote astronomical observations of the aurora, trying to correlate those observations with inferred solar wind inputs. And in the case of the outer magnetospheres, the same thing happens. The driving of the thermosphere by the ionosphere imposes a much slower time scale on the system than just the magnetosphere-ionosphere coupling. And it's the relative motion between ionosphere and thermosphere which drives currents, which produce nice things like auroras.
Right. Yeah, I agree.
What's special about 15, 20 minutes timescales? And does that depend on IMF conditions?
That's a good question. I don't, presently I'm not aware of any particular reason why it should be that time, except that that is the typically observed residence time of a flow burst in the ice-cat radar, for example.
Okay, I guess that's it for questions on this thing.